Greetings, everybody. My name is Yinghao from University of Tsukuba. Today, I will introduce my research titled Surgical Operation Assisted Imaging System using multi-view technology. So let's start. In order to obtain higher quality and complete images of surgical details, we proposed such a photography system in which multiple cameras are sited between the doctor and the patient. In order to obtain a more informative video of the surgery and to analyze the procedure better, we try to capture and generate a multi-view body time video. So first of all, surgical recording systems often have many new meanings nowadays. For instance, it could help with sharing of education and surgical techniques. And we're facing with individuals in this study and performing medical evolution. For now, the previous system can be divided into three representative ones so far. The first one is boom suspension capturing system. It can be seen as the most traditional way. And the second one is the shadowless lamp-mounted capturing system, which was designed not long ago, and it was a great idea. And for the last one is head-mounted capturing system. It's not only medical, but other fields are still very useful in a long history. So, however, the existing surgical imaging system always has different problems. For the first and second one, we found that in these ways, almost impossible to record the specific procedure of the operation. It means occlusion often occurs, so that sometimes it is impossible to record the details. And the image quality problem and viewing angle problem caused by the instability for the last one. So as for this problem, we designed our proposed system. What technology do we mainly use? I think it should be the body time capturing technology. We all know that multi-viewpoint video technology uses multiple cameras to capture image or videos. In this way, we could obtain a full range of images to meet the needs of subsequent processing. It allows for the avoid of obstacle in the shooting path received by a single camera by designing a good trigger sequence. And combine each frame of photos taken by each frame can form a perspective rotation effect on a stationary object or super slow motion effect, just as the demo body time video show. In theory, the virtual camera can achieve unlimited viewing angle and frame refresh rate. And body time has a wide range of application in many fields today, such as sports match broadcast, filming, and game development. So next, this is our current workflow chart. First, before the operation starts, we install our camera system between the doctor and the patient. Then we adjust the parameters such as the head of the camera and connect it to the prepared computer. During the surgery, we switch the camera to choose the best view in real time. Target detection technology will be used for how to determine the best view at each moment. Then we transfer the acquired images to the computer through the high PCIe port. These images will be saved according to the camera number and the shooting time. After series of image processing and then rearranged into a body time video. It will finally be played on the surgical video monitor. The system we proposed can be divided into two parts: image capture system and image processing system. Next, I will talk about them by order. In order to apply multi-viewpoint technology to surgical video capturing, we propose such a novel surgical recording system. The system has 20 USB camera module and the LED strip lights, including 60 LED lights and 20 sports lights with special designed light controller. And next, I will mainly introduce how the recording system works. First, we developed a multi-view camera control program using the MATLAB and Python. We use the OpenCV to do the image processing and MATLAB library image occlusion toolbox to set the camera control. The program has a function of previewing the real-time images of each camera, capturing image and videos, and can also switch cameras. In order to improve the interoperability, we designed a simple interface by using Qt5. The system uses the SFM method to perform camera calibration. First, we start all the multi-view cameras for image occlusion. The order in which the cameras are numbered corresponds to their actual position in 3D space. By importing the images taken by the multi-view camera, the camera parameter are obtained and the image feature points are extracted. The position and the order of the camera are estimated based on the corresponding point information, and the 3D position of the corresponding point is estimated through stereovation. After that, the intrinsic parameter can be used to calculate the image rotation matrix. As for the extrinsic parameter, can help with presuming the camera position and gesture. And next, it's time to talk about YOLO wave4 detector. The purpose of using it is to set the gaze point to generate the body time video. And the order to is prepare surgical image data, then annotate the image data, and final do the object detection and get the detection result for each object. The reason why we choose YOLO wave4 is that it requires simple environments to train model, and it can achieve faster speed, relatively better accuracy than the previous version. In order to be able to detect the target, for example, the surgeon's hand, surgical field, surgical instruments more accurately, the YOLO wave4 algorithm was trained on a special dataset that the resolution is 1080p, contains 1218 keyframe images, and the size is 250 megabytes, and all the ground truths are manually marked using YOLO mark. So in order to let the gazing point be observed at the center of the images in the generated video, we need to warp the camera frames by a homographic transform. As shown in this figure, we let the O be the image center of the original image I, and the P be the projection of the gaze point on image. Then the vectors small a and b represent the vector in 3D space from the camera's optical center to O and P respectively. So we can get the unsuited rotation matrix. And with the help of camera calibration results, what we have got before, we could easily get the intrinsic matrix AI. The small I here represent the camera ID. Finally, by the following equation, we could derive the transformation matrix H. And body time video is generated by image switching of a multi-view camera. Normally, the surgical videos are shown in the main view. Once you are facing with a critical moment according to the surgery procedure, it could be the a certain time point of excision, homeostasis, ligation, and searching, especially for the performing time. So you can choose the trigger. You can choose to trigger the body time function in the program to generate the corresponding video to observe and analyze what is happening at the moment better. Fortunately, we have kept the processing time as short as possible to make the generation can stop and start at any time. As for the system latency, it's mainly divided into 4 parts below and ordered by the short time, long or short. Data transmission limitation of USB 2.0, runtime of MATLAB, camera switching time, and image processing time. So when talking about the detector, YOLO-V4 is a new version algorithm, and there has been almost no research about surgical detection based on it before. So we designed this experiment to test its effect in recognizing several objects in the surgical scene. In this experiment, we use the described data set to do target detection. About the images, we capture a video string. It's a 21-second video and 30 frames for each second. And then we use the FMPG in Python library. For each second of the footage, 8 frames were extracted based on IPB method to get the keyframes. So totally 168 images were obtained. Just as this figure shows, the experimental process and the general appearance of the target to be detected are shows. And our experimental results show very different detection rates for different detection objects. This table shows detailed results of our detection task. Among all the objects, the surgery field operation area is the highest performing object, mainly due to its, we can see, apparent features that are easy to detect. However, the low performance of searching forceps is mainly due to the posture diversity actually used as the minute marking areas. And similar appearance characteristics cause the surgical instruments to be misdetected as each other sometimes. It could be the reason. And here finally comes to the conclusion. First, we construct the proposed system prototype for the capturing system in order to decide the type of camera module, LED spotlight, and the computer. We designed several comparison experiments and compared the several camera light computer of several brands. And solved the control problem of driver-free UVC camera and developed a camera and LED control system to realize parent transfer. And about the image processing, we use the SFM method for camera calibration with the help of CodeMap and train our own model for UV4 target detection. At present, the gate point is set precisely on the basis of coordinates of the detection of the detected object given by YOLO detector. In our consideration, in the future, we will build on the existing research to improve the latency and the accuracy of the gate point setting, and on the other hand, import the real surgical scene data to try to identify and solve the problem caused by the differences between the real data and the ideal data. So that's all. Thanks for listening.